So it's been about a month or so since I made my last video on the calorie. Really proud of that. You might want to check that out. So I thought I was going to be making a much quicker video on the hydrogen bond, a classic but somewhat misunderstood term in first year chemistry. Now, I knew that the first year definition of the hydrogen bond was always oversimplified and a bit problematic, but I didn't realize how oversimplified and problematic it was until I started doing more research. I mean, it was sort of like one of those home repair shows where every time you look behind the wall, the person goes, uh-oh, that's not good. It got to the point where it was a little absurd. Every thread I pulled about hydrogen bonds unraveled everything I knew.
But when I pulled on one of those threads, it unraveled the tapestry of my life.
From their very discovery over a century ago, people have been struggling with what exactly a hydrogen bond is. The International Union of Pure and Applied Chemistry, the IUPAC, sort of an oversight body of chemistry that helps with like naming elements and correcting terminology, put together a working group 10 years ago to try to solve this very problem. So let's start with how hydrogen bonds are typically presented in an introductory classroom. And this is probably the definition you know if you know any at all. Well, we usually tell people that they really aren't a chemical bond despite the name. They are the strongest of intermolecular forces. If you have molecules with unequal distributions of charge, they can be attracted to each other physically. And the hydrogen bond sets up the strongest of these interactions. It is what's involved with DNA being able to split and replicate. Along that seam are physical hydrogen bonds, not chemical bonds. These weak forces are what makes water a liquid at room temperature. If it wasn't for hydrogen bonds, all the water in your body would turn into a gas and all life on Earth would die. So kind of important. Now, this does get weird. It might depend on how you define bond. Hydrogen bonds can technically be defined as what are called weak bonds or secondary bonds. But maybe we shouldn't kick over that hornet's nest in this video. If we want to talk about the whole spectrum of bonds, we're going to need a bigger video.
You're going to need a bigger boat.
What causes the hydrogen bond, what causes that strong molecular interaction is the fact that we have hydrogen, hence the name hydrogen bond, bonded to what's considered a highly electronegative element, like nitrogen, oxygen, or fluorine. And what these highly electronegative elements do is they pull the electron cloud away from hydrogen. And why hydrogen is so important is that most atoms, when you pull the cloud away, you reveal more electrons. But when you pull the cloud away from hydrogen, you reveal that proton. So what you get is an unusually strong physical interaction between molecules. Now, hydrogen bonds are still presented as much weaker than traditional chemical bonds. The bond between oxygen and hydrogen in water, for instance, is about 112 kilocalories per mole in strength. The hydrogen bond between molecules are only about 5 kilocalories per mole. So there you go. That is the classic first year chemistry definition of the hydrogen bond. So what's wrong with that? Well, I can think of 5 things. Coming in at number 5 is the idea that they aren't just intermolecular forces. We usually introduce the hydrogen bond as a really strong force between molecules, like handshakes between 2 different people. But you can shake your own hand, can't you? A molecule does not have to be that big to have intramolecular forces, forces between different parts of the molecule. You might remember this from biology class. Not only do you have the protein, but you have secondary, tertiary, and quaternary structures, and hydrogen bonds are among the forces that create that 3D structure. Coming in at number 4 is the idea that hydrogen can be bonded to way more than what is traditionally presented. Now, I've taught thousands of students that hydrogen had to be bonded to nitrogen, oxygen, or fluorine. Only they were electronegative enough to pull the cloud away and create that hydrogen bond. It just turns out I was wrong. I mean, electronegativity doesn't stop at nitrogen. Other elements can still pull electrons away from hydrogen. And so research has shown that although the strength of the hydrogen bond involved with other elements is weaker, it's still there. They have measured this with elements like chlorine, sulfur, even carbon. Even carbon can pull enough electrons away to make a weaker hydrogen bond. Coming in at number 3, the hydrogen bond acceptor matters also. So remember, it takes 2 to tango. Just like there is a spectrum of strength of the H bond donor, researchers have found a whole spectrum of strength of H bond acceptors. Anywhere from ions to less electronegative elements like sulfur, all the way down to electrons found in double or triple bonds, pi bonds, as we call them in the business. So it shouldn't be a surprise coming in at number 2, hydrogen bonds can be way weaker than presented in first-year chemistry class. Remember that the classic hydrogen bond between 2 water molecules is presented as about 5 kcals per mole. When you start looking at interactions between things at the bottom of the H-bond acceptor and donor spectrum, that strength goes down an order of magnitude. They have measured hydrogen bonds down to 0.5 kcals per mole. So the flip side of number 2 is that hydrogen bonds can be way stronger than presented in first-year chemistry. If you take H-bond donors and H-bond acceptors at the top of that scale, then you are approaching the strength of a covalent bond. 6, 7, 8 times as much as the hydrogen bond present between 2 water molecules. It's crazy. Take, for instance, bifluoride ion, FHF-. That's right, that's hydrogen making 2 bonds. Now, I don't know about your chemistry class, but I've told my chemistry class that hydrogen never makes more than 1 bond. In fact, if you give hydrogen a double bond in my class, you might as well give me the middle finger because that is how offensive that is. Well, fingers away. In fact, the hydrogen bond in a bifluoride is almost 40 kcals per mole, and that rivals the strength of the weakest covalent bonds. That hydrogen bond in bifluoride is so strong that that complex is presented as 1 chemical formula. Now, if you haven't had enough, I'll give you what I'll call number 0, and that's hydrogen bonds don't even need hydrogen. They have found similar interactions when you replace hydrogen with a halogen, and those are called halogen bonds. You can replace it with a chalcogen, oxygens group. You can replace it with a nitrogen and find a pnictogen bond. It's turtles all the way down. So where does that leave us? What did the IUPAC present as the new definition of the hydrogen bond back in 2011? Well, here it is. I got a better idea. Hydrogen bonds, they're complicated. I reached out to many of the scientists involved with that IUPAC paper on redefining the hydrogen bond. One of those scientists was kind enough to offer to continue the conversation over Skype, and I jumped at the opportunity and I recorded that. And so I hope you check out my interview with Dr. Scheiner. He was warm and generous and funny, and I had a great time talking to him. Thanks for watching, stay safe, and have a great day. And it will not take a month to get to Chem Troubles number 2, I promise you that.